In this section, we're going to look at ways that we can extend the concept of integration to not only calculate areas of regions, but also volumes. One method of doing this is called the disk method, and it allows us to calculate a volume of an object created by rotating a function around an axis. So for instance, let's suppose I have a very simple function, which is just a constant function, and it produces a rectangle on the x-axis. Okay, now what I'm going to do is I'm going to take that rectangle and I'm going to rotate it about the x-axis. So I'm going to take that and just rotate it all the way around. And I'll draw this as best I can, but you'll see how this turns out. All right, so ultimately, this will end up looking something like this. So we have our rectangle, and as we rotate it around the x-axis, it will form a path. It's going to sort of look like ellipses, and I'm not great at drawing things in 3 dimensions, so you'll just have to bear with me the best that you can. That's actually not too bad. All right, so essentially what we've done is we've taken this rectangle, which has a particular height, and it has a particular width. The height of the rectangle ultimately is going to be defined by some function, but we can kind of think of it as a radius. All right, so how far away we are from the x-axis. And then the width, because we're ultimately going to work into integration, the width we can think of as our little friend delta x. And that way we can control how wide these rectangles are and get better approximations through time. All right, when we do the rotation, we still have delta x along this axis here. I'm going to center that. Let me try again. Okay, and then also, this is still a radius. And let me switch colors so you can see it better. Now, the face of this disk. Right, so if you just think of one part of it, so just this part right here. And the reason I'm only thinking of that part is because ultimately we're going to let these rectangles go to 0 width in order to take an integral. So you kind of think in terms of like a rectangle that has a width to make sense of how we're doing this calculation, but ultimately, you know, you're going to do your calculation based off of a slice of the function. So a slice of this function at a particular point is defined by some sort of surface area function. So I'll just say like a of x, so some surface area. And then if you multiply that by its width, so this is no longer just the height, it's a surface area, but you multiply that by width, and when you multiply area times another dimension, you get a volume. So you get the volume of this particular disk. Now we can actually do even better than that, because this disk, even though I have to draw it as an ellipse for 3D, it's actually a circle. And we know the circle here would have an area of pi times the radius of the circle squared, and then we'd still multiply that by delta x, and that gives us the volume of one particular disk here. Okay? So that's easy enough to see where the volume of one of these disks comes from. All right, now if you imagine you have a function f of x and you're rotating that function around the x-axis, and I am not going to be able to draw that at all, so let me bring up something to help us see this visually. Okay, so here's an app that has drawn a function for us in the xy plane, and it's really just a parabola, so x squared, but it's only drawn between 0 and 2, and so you're kind of seeing the top of it here. Now, what I want to do is I want to take this function and rotate the entire function around an axis. So you could use either the x or the y axis. I'm using the y here just because it's oriented that direction. But the rotation, what happens is, as you rotate it, you'll get a solid object. And you can't really see it all that well from this angle, so let's move it around a bit and take a look at it from a different viewpoint. So that's the solid that we create. So just you can see it again here. We start with this function, x squared, and we rotate that function around the axis and produce this solid object right here. So what we're ultimately saying is that we can use this process of taking just a single rectangle and extend it out in order to come up with the volume of this entire object. We would have to use multiple rectangles, and unfortunately I can't do this in this software, but the more rectangles we use, the better approximation of volume that we get, and ultimately, using an integral, we can come up with the actual volume of this object. So that's where we get the following formulas. The volume of a solid of revolution using the disk method is either going to be v equals the integral from a to b of pi times a function r of x squared dx, if we happen to be rotating around the x-axis, or the volume is the integral from a to b of pi times r of y squared dy for rotations around the y-axis. But notice the similarity in the formula that we had before. We ultimately have the area of a circle, and that's what's being produced with the disk, and we're getting the area of the circle through this function, and the function is, instead of the radius being constant, the radius is defined by a function because it changes from one point on the axis to another. But we take that and multiply it by dx, which is our term delta x, what we were using for the width of the rectangle, and that area times a width gives us a volume integral. So this is how we would come about determining these volumes. Now, let's see how it actually works through an example. All right, so the first example, we're going to use the disk method in order to find the volume of a solid revolution generated by rotating the region between the graphs of f of x equals the square root of 4 minus x and the x-axis over the interval 0 to 4, and we're going to rotate around the x-axis. Okay, so you're absolutely going to need to see what these graphs look like in order to work through the problems. The very first step in the whole process is going to be producing a graph of the region. All right, so let's see. I'm going to draw it like this. All right, so there's my x-axis. I'm on the interval 0 to 4, so we'll say 1, 2, 3, 4. That would be great. That's probably enough there. All right, now the graph of the square root of 4 minus x. If you're unsure what that looks like, simply grab your calculator and have your calculator sketch it out for you, and then you can use that as a starting point. Oh, but I'm in the wrong mode. Let me get back to function mode here. All right, so if we want to see what that looks like, we would just simply graph the square root of 4 minus x. Okay, so square root graph, basic graph, but it's pointing backwards, and it's shifted to the right 4 units. Okay, so we have a point here, there's a point here, and the graph looks like that. Okay, we're rotating around the x-axis, all right, and we're on the interval from 0 to 4. All right, so I have these other bounds then, basically, where x is 0 and x is 4. And then sort of implied, because I'm rotating around the x-axis, I also have an additional bound here of y equals 0. Sometimes that will just be implied, and sometimes that will be stated. But regardless, this is the region that I'm rotating around the x-axis here. So this region right inside here. Okay, now to do this, what we would like, what's a good idea here is to just draw a single rectangle and orient the rectangle either vertically or horizontally. All right, and one thing to keep in mind is if you choose rectangles that are oriented vertically, then you will be integrating dx. If you are orienting your rectangles horizontally, then you will be integrating dy. So you'll need to sort of make a choice there sometimes, but you know, the way I do it is I will use a vertical rectangle unless there's a good reason not to. So I generally will just try a vertical rectangle to start with. All right, so there's one rectangle that I'm sort of thinking in my head of rotating around and making that disk. All right, so the height of this rectangle defines this function r of x, because when I go to get my volume, I would be using the integral from a to b of pi times some function r of x squared dx. And it would be dx because I'm using a vertical rectangle, and then that way I know my function is in terms of the variable x, so r of x. Okay, so this actually isn't nearly as bad as it might seem to be. So what I'm going to do is set up my integral. So my rectangles would start here at 0 and finish by x equals 4. So I would integrate between 0 and 4. And then I have the constant pi. The function itself is the height of the rectangle. So that's my r of x, which is 4 minus x. So at any point for x, this tells me the height of the rectangle. That gets squared. Then we integrate dx. So essentially, I'm doing the integral from 0 to 4 of pi. Squaring a square root cancels, so then I have 4 minus x dx. Now, we've been using fnint in order to calculate our integrals, and if we did that with the constant pi, what would happen is we could never get a final answer that is a fraction. Let me show you what I mean. So if I integrate this, so math9, go from 0 to 4, and my function here is pi times the quantity 4 minus x, and then integrate dx. All right, so when I do that, I will get an answer, but if I try to change that answer into a fraction, it won't do anything. And that's because this is an irrational value. When you multiply something by pi, which is irrational, you get an irrational answer, so you can't convert it to a fraction. By definition, if a number is rational, it can be written as a fraction. If it's irrational, it can't. So we can't get an exact answer here with the way we were doing things. But there's a really easy fix for this. This number pi can be factored out of our integral because it's simply a constant. And what I can do is I can get the value of the integral part that is rational. So go under math and 9. Whoops. Pressed enter one too many times. Okay. So I'm integrating from 0 to 4 of now just 4 minus x dx. All right. And that actually gets me a whole number, so that's fine. All right, so all of this then is equal to 8. So essentially, I have pi times 8, or 8 pi, which is the same answer as I had previously. It's just now I have an exact representation of that answer. So, same result.